would start probably not from Charles Darwin, but from his grandfather, who was a physician and actually wrote a poem about the origin of life, where he indicated great priority of energy, first of all, sunlight, etc., and then birth of the planets, and life would spontaneously appear in the ocean. Charles Darwin, of course, didn't touch this problem of the origin and early evolution of life. First of all, because at that time, paleontology actually was related only to the topmost part or latest part of the fossil record, and maybe 85% of the fossil record was unknown by that time. For Darwin it was a great problem, and in a way complex of inferiority related to this abrupt appearance of species at the beginning of the Paleozoic time. But today I would like to speak not so much about the, let's say, origin of species, etc., but rather on the physical aspect of the evolution. And I would start with the metaphor which was suggested by Leonardo da Vinci, who compared organism with the flame of the candle, which actually burn this wax and then produce foam, and this sustained body of the flame is an organism. Geochemistry, great French paleontologist, also suggested interesting metaphor in terms of life. He said that organisms resemble tornado, which has all features of the living being. It moves, it is growing, it consumes and throws out. It can even reproduce, divide. So all sorts of features of the living being. But this beast exists while the wind is blowing. When energy wind stops, then this structure disappears. Well, this is very useful metaphors. They show us the priority of energy flow in the life processes, and of course in terms of the quantum mechanics, for instance, or physics, we know that non-equilibrium, that means the flow of energy of matter, can be the source of the order and source of kinetic stability of the structure at the molecular and higher levels. Today we should probably talk from the point of view of this primary role of the dynamic physical aspect of the origin of life and early evolution. And of course it is rather unusual that we would use a bottom-up approach, so from the beginning and on, and we shall attempt to consider the system of organism and environment as a one system actually of the processes, as a complementary processes. But first I would like to start with indication of water, which appeared very early on our planet, probably over 4 billion years ago. The fossil record, of course, is not older than, let's say, 3.8. And the sources of water on our planet were, of course, degassing of the interiors and the comets' space supply of the planet with water. You know, our planet was very stark and unfamiliar for us if you would visit it. Radiogenic heat was very high, maybe 10 times more high than at present. Moon was very close to our planet, and it was actually, it produced mechanical heating of the interior. Then, of course, high heat caused intensive volcanism and full recycling of the Earth crust. Relief was very low because Earth crust was very thin and when water appeared, it appeared as a thin layer all over the globe because absence of volcanoes. You see here, you see that dynamics of heating of different elements, including potassium 40, and decline of that. Here is just schematically show that indeed Earth crust was very thin and high relief was impossible. It was high temperature. The atmosphere was separated with the greenhouse gases, including CO2, carbon dioxide, methane, and hydrogen sulfide. On this scheme, you see the intensity of the crustal growth through Earth history from 4 billion years up to present, and of course, appearance of the continents. This volcanic activity actually slowly declined, but still there were some peaks in the later history. So you see, at that time, sun luminosity, as predicted by cosmologists, by astrophysicists, sun luminosity was about 30% lower than at present, but this low luminosity was compensated by the greenhouse effect of the atmosphere, which actually kept our planet hot quite long ago, till about 2.2 billion years ago. There were no glaciations. Relatively rapidly, during probably the first 100 million years, the metal core of the planet was formed, and that means the magnetic field was in place very early, about 4.4 billion years ago or so. Of course, it was reducing atmosphere and no traces of oxygen at the very beginning, and that's no ozone screen, of course. On this graph, you see this dynamics of the metal core formation of the planet, as depicted by Galinov. I should mention, of course, our nearest star, Sun. Unlike this massive stars, it was small enough, and it produced not only, of course, some metals, but also its photosphere contains the dominating part of hydrogen and, of course, helium. But important also that it contains some metals, including iron, which is quite a large number, large volume in the photosphere. I mentioned hydrogen because hydrogen actually plays a key role in the microbial metabolism, and on this molecular tree of microbial life, we put the archaic periodic table to stress the central position of hydrogen in energy metabolism. First of all, of course, hydrogen, is the most abundant chemical elements in the universe, and it could be primary fuel of life, just because, not because only that it is part of water which dominates in every living being, but also because of soft hydrogen bonds which provide stability and versatility of the macromolecules. And of course, many recent microorganisms use hydrogen as a source of energy. Of course, we have heard already that proton gradients are used to process, in the process of ATP generation. Many microbes use, or enzymes perform proton transfer. It's very important that molecular hydrogen is a key intermediate product of anaerobic metabolism, and it makes, I would say, energetic trophic connection between microbes which live on different substrates. So, in a way, hydrogen is an energetic currency between different microbes which live in communities. So it is, I would say, ecological factor, arranging factor. Here you show that bacterial part of the tree of life, and in the red you see this, those bacteria which use hydrogen directly. I probably could continue on and on about this role of hydrogen in microbial metabolism. It is used also in catabolic and anabolic reactions. It is phototrophic bacteria, for instance, can produce or consume molecular hydrogen, etc. Here on this graph, you see different kinds of hydrogen metabolism, I would say. And very common that if those reactions of hydrogen with different different elements are catalyzed by the transition metals, first of all, iron, manganese, nickel, and also tungsten, and that's important. We shall come back to the metals later. So you see, what the near universality of hydrogen metabolism of microorganisms, and of course high similarity of the structure of the enzymes, well, may hint that hydrogen had great importance at the very beginning of life, and maybe even in the process of the origin of life. You see, most of reactions in the cell are basically electrochemical, and hydrogen makes a proton and electron is just ideal source for life. But interesting enough that in this part, which shows the reactions of Red's reaction of hydrogen and its compound, it coincides also with iron respiration in bacteria, and this may be symptomatic. You see, prokaryotes, of course, may be the most ideal electrochemists. They embed their metabolism into the natural electrochemical gradients very often. And of course, you probably hard to see, but you may see that in eubacteria and archaebacteria, which are known only maybe a small segment of their diversity, a lot of these species, of these reactions, involve hydrogen or its simple compounds. At present, in nature, there are a few sources of hydrogen, both like, for instance, magma-host systems, the gassing of the interior, process of serpentinization, I will tell later, but also some biotic phenomena like photosynthesis, fermentation, carbon oxide oxidation, produce hydrogen, which is used for microbial activities. Just to show you one example of serpentinization, which is a reaction of aluminum peroxide rich rocks with water at low temperature, about 400 degrees, and it produces magnetites and the serpentin minerals and liberate molecular hydrogen. I will probably miss details of this process, which is well known at present. It requires, of course, water temperature, and it is hydrogen release from the hydrothermal system is common both in the ocean and on land, and this is a very common example from these hot springs in Idaho. And you see, in this simple reaction of oxidation of hydrogen CO2 with making methane and water, and archaebacteria, you see they are dominating in these environments. Archaea, it makes this one of the longest branch of the, well, suppose that life could appear indeed in those hot vents. And indeed there are many models now which consider hot vents on the ocean floor as a cradle of life. For instance, Michael Russell develops these ideas, and he operates with the crust, mineral crust. So this is bubbles made of pyrite or actually ferrum sulfate, which were first granules, proteinish bubbles, things like that, and maybe they produced first prototypes of the cell. But from the physical point of view, I think interesting that this hydrothermal environment, first of all, was electron-rich. It has sharp electrochemical gradients when you move from the sediment to the water, and it has abundant metal ions, and of course molecular hydrogen in its volatile compounds, which are the major substrate for many bacteria till present. On early Earth, I think the sources of hydrogen were more numerous and I would say more productive. It is, of course, the gassing of the mantle, and of course that serpentinization of the volcanic rocks I described earlier, photolysis of water by UV radiation, and radiolysis, that's splitting of water by the energy, radioactive energy. Then, of course, all sorts of dissociation of water in the interior, including bombardment of hydrocarbon and bright alpha particles. So there are quite extensive list of the sources of hydrogen on Earth. Experimental minerals show that well, these meteorites certainly made the primary body of our planet, and heating of those meteorites under high pressure caused a release of hydrogen, and there are interesting experiments related to the origin of the metal core. This process should be accompanied by the high release of hydrogen as well, and having in mind that all metal core was formed very fast, this primarily emanation of hydrogen could be fast as well at the very beginning of the geological history. Some calculation by Tian and his colleagues showed that hydrogen, though it is a very volatile element and it's escaping our atmosphere, but still it could make up to 30% of ancient atmosphere. Well, there are other calculations as well, but what I would like to stress that, of course, hydrogen very easily escapes from atmosphere, but in the fluids inside the rocks and the sediments, that concentration of dissolved hydrogen and its compound could be very high, and hydrogen gave easy access to protons and electrons, the very motor of the cell energy machine. At present, we know that biochemical reactions that involve hydrogen are catalyzed by metalloenzymes, and this is iron and iron-nickel dehydrogenases. These enzymes catalyze very simple, maybe simplest of the chemical reactions, with reversible reductive formation of hydrogen from protons and electrons. That's the key in the first reaction, and which still works in the living cell. Most of these enzymes of dehydrogenase are found in archaea and bacteria, but a few are present in eukarya as well. Iron hydrogenases are restricted only to bacteria and eukarya, but nickel iron hydrogenases are known in archaea only. That's a mistake. In archaea and bacteria. So that may indicate that nickel enzymes are more archaic, and maybe it is kind of relict of the Hadean Archean times. Hydrogenases are huge protein molecules, and they contain these so-called metal centers, which transport proton and release hydrogen and, of course, electrons. So they pass energy flow through these molecules, and these active centers have structures which contains so-called Q bonds iron sulfur cubons. Or sometimes they have double iron, which is coordinated by sulfur, also very interesting. Sometimes they have iron and nickel, also coordinated by sulfur and pistons connections to the protein molecule. So these cubons resemble crystal lattice or such mineral like gray grit, for instance. That's iron nickel sulfate, which is formed in present day in the hot springs, or even pyrite. So again, it is kind of a hint that these kind of enzymes, or their active centers, would be synthesized abiotically on the primary Earth along in the hydrothermal systems. You know, we have to pay attention to the history of volcanism, and the most mafic rock, this oil, rich with metals like chromium, cobalt, nickel, iron. This kind of volcanism was very common for early stages, and then it became more and more light, I would say, and less and less rich with metals. So truly, early volcanism provided a lot of catalysts into the environment. And we know that in present day, enzymes, metal plays a central role. This is porphyrin ring, for instance, and depending on the kind of metal inside, if it is magnesium, it will be chlorophyll. If it's iron or copper, it will be cytochromes. Hemoglobin, this is iron, etc. Nickel, it's hydrogenases. So you see, it is wonderful invention, but metal changed its role and is becoming very, I would say, valuable because the whole proteinish molecule is trying to save it from oxidation, and literally every atom is counted because it's very valuable. Key example of this growth medium for cyanobacteria, you see how much they require magnesium, and mostly because chlorophylls and bacterial chlorophylls, for instance, they are based on magnesium. It looks like that preferences of the metal, especially in the photosynthesis, might be related to the photosphere I mentioned. It has some amount of iron and magnesium as a dominating metals in the photosphere of the sun. And though, of course, chlorophyll use only very narrow a part of the, let's say, whole spectrum of the radiation, inside this spectrum, they have some maxima and minima. And you see the purple bacteria and green sulfur bacteria represent so-called unoxygenous photosynthesis, and cyanobacteria is oxygenic photosynthesis. And you see they are, as if they're shifting along the spectrum, and quite possible that this picture can be interpreted historically, that this kind of chlorophyll predated the green sulfur chlorophyll and then cyanobacterial chlorophyll, which unites two of the systems. So it's quite possible the whole evolution moved towards the violet part of the spectrum, but light is dangerous phenomena, and interesting enough that this antenna, light harvesting antenna, they are sitting in the minima, which correspond to the brown wafer lines of the spectrum. They are sitting there like soldiers in the trench, and they modify their molecules to get a few quants of light and then hide again. And that's probably the most safe way to survive, because UV radiation, especially dangerous for DNA and other biomolecules. And it looks like that photo harvesting antenna are tuned to the sunlight spectrum via the metals. It is actually like a radio receiver to a radio station. And that's important. And for us, and for physicists, the interesting question, how sun photosphere actually evolved through time. And what was the beginning? It is interesting question. So you see photosynthesis, and again on the molecular appeared relatively late. I mean, many groups of these groups perform photosynthesis, but oxygenic photosynthesis was probably the last one. It is very complex, combining two photosyntheses existing in different branches of bacteria. And this was, of course, a revolutionary phenomena in biosphere because it immediately put those valuable metals, those catalysts in a very difficult situation. On early Earth, of course, nickel and iron and maybe tungsten were quite abundant and available, but as soon as, well, I will mention a little bit about tungsten. It was discovered relatively recently, like nickel. Interesting then, tungsten is so far known only in prokaryotes, and only hyperthermophilic archaebacteria or archaea are obligatory dependent on tungsten. That's again a hint to direct our attention towards the hydrothermal system where life would rise very early. So tungsten enzymes could appear also very early and on our planet. But oxidation of biosphere, which especially intensive became, let's say, after 2.5 billion years ago, and it was also cooling. That is why the first glaciation also 2.2 billion years ago, and oxygen is better dissolved in cold water. So we see that this is dynamics of the oxygenation of our atmosphere. And while it is oxidizing, then while some metals became less available, like iron, for instance, nickel, but others like zinc and copper or molybdenum became more available due to the better solubility of their compounds, their oxides. So this dynamic shows this decline of availability of metals because of the different solubility. So the whole global ecosystem had to change metabolic pathways, somehow modify them, and actually it was beginning of the growing complexity. Well, these episodes of massive ore deposition, like manganese or iron or uranium, those elements which are sensitive to oxygen, meant that oxygen was already quite, intensively produced by cyanobacteria, and that means this metal became less and less available. That means I have 5 minutes, right? 10 minutes.
Including discussion.
Okay, thank you. So, but not only oxygen, of course, caused this change. Nature volcanism also changed because of lowering temperature of volcanism caused less release of nickel. And nickel, is a very important catalyzer in those enzymes which catalyze methanogenesis. And that means production of methane decreased dramatically, and greenhouse effect also fall down. So here, this is a succession of the metals which were gradually involved into the metabolism, with their growing role in the Earth history, which I reconstructed some years ago. So all sources of hydrogen decline, first of all, but also sources of the primary metals like iron and nickel also decline. And that stimulated actually the cell to switch from hydrogen to hydrogen compounds, such as hydrogen sulfate, methane, or ammonia, and at last water. But you know, to split those molecules, it takes some energy, it takes some enzymes, of course, and this is, shows these reactions of source of electron and its acceptor of electron. It takes creation some redox potential, and if we look at this graph showing reactions of hydrogen and methane and ammonia, for instance, and then splitting of water, and it is huge potential. So quite possible that here we may have a succession again, historical succession from 4 billion years ago to 2.7 billion years ago. So bacterial world learned how to split hydrogen compounds up to the splitting water in the oxygenic photosynthesis. And byproduct of this evolution was, first of all, nitrogen and oxygen atmosphere. Enormous amount of nitrogen and oxygen shows that these byproducts of the nitrogen side oxygen not quite hooked to each other. This decreasing amount of hydrogen caused a kind of, or forced, I would say, bacteria to make a kind of symbiotic systems that would be pick from each other. And first of all, cells tried to save archaic biochemistry by isolate them in time, or literally in membranes, vesicles, organelles, etc. And to prevent those motors, primary motors, from oxidation, but also the mechanism of scavenging, storage of metals internally, and of course unation of the complementary metabolic pathways. And symbiosis of prokaryotes became very common by the time, and that actually caused increasing complexity, because you know, in order to be one cell, for instance, of different symbionts, they should tune their reproduction, their feeding, and many other things. So I would say that what this beauty, this immense complexity of the eukaryotic cell with all these sorts of organelles, it is in a way miniaturization of the pre-existing ecosystem with different kinds of bacteria inside one cell. It is just indeed an incredible complexity, and it takes a lot of evolution. There are many hypotheses, maybe 20, 25 hypotheses on the origin of a eukaryotic cell, but I would give preference to those of these hypotheses which deal with the, which are based on the syntrophy involving hydrogen. And like here, for instance, one bacteria produces hydrogen, another consumes it, and they go together and they then make one cell, and they literally count and save every proton from hydrogen. And the result of that was this large and very complex cell with many compartments. In every compartment, try to save archaic kind of biochemistry. On this graph, probably you see how life evolved depending on the hydrogen from hydrothermal, and then, of course, biologically produce hydrogen, and then oxygen appears as an electron acceptor, etc. So I think we underappreciate hydrogen metabolism, and it is growing attention to its role in evolution. one of the tasks of paleontology and molecular biology is to reconstruct evolutionary processes. Here on the left you see the fossil record where they date major events like appearance of photosynthesis and, oops, excuse me, that will come back. Yeah. But interesting that molecular clocks very often give more older dates in terms of some events like, for instance, origin of photosynthesis or split of animals and plants. And this, let's say, aging, not aging, but larger number of time, greater age, I would say, is based probably or dependent on the all sorts of symbiotic events, symbiogenetic events, and that is why molecular clocks show older dates in evolution. Another source, I think, very interesting source, is attempts to interpret the metabolic cascades in the cell in terms of its history. It looks like that cascades of these metabolic reactions and those modules in the metabolic pathways recapitulate in some extent the major biogeochemical events in the past. And this is very difficult but very promising way. I would like to finish my presentation with quoting from the book by Barrow and his co-authors. It is Anthropic Cosmological Principle, and they show that, well, sooner or later life will exhaust our planet and move to the space, and will actually involve new and new sources of energy, including gravitation, for instance, gravitational energy, and then sooner or later it will occupy the whole universe, and the whole universe will be the biosphere, and then it will reach a mega point, as maybe you know, Teilhard de Chardin, his beautiful books. Well, anyway, we shall see. So I would like to finish with the notion that very often people compare life with the music, especially with fuga, or future, that repeats some themes, etc., and develop them. That's probably true for the latest part of evolution, but early part of evolution, original life, probably was different genre. It was rather hydrogen and heavy metals. Well, thank you very much for your attention.